Hello class, today I'm going to solve one sample question for session 5 material, and for this one let's solve and find Jacobian matrix for this quadrilateral element. Okay, so as you can see, this element has 4 nodes. Node number 1, then number 2, number 3, number 4, and we name these nodes counterclockwise. It doesn't matter which direction you name them, but you need to be consistent and keep that naming consistent all over your solution. So let's see what is going to happen if I convert this xy axis to normalized axis of psi and eta. So let's draw it. This element is going to be converted to something like this. This is my psi, eta. We know because these two axes are normalized, they should be from -1 to 1 like this. Therefore, the element is going to be something like this. -1 and 1 for one of them, -1 and 1, 1 and 1, and -1 and 1. So let's connect those dots to each other. So now you can see how normalized axis can help us to convert this angled element, which could be any shape, to very nice element with vertical sides, which would be much easier for us to solve. Okay, no extra information, we already know those things. Let's start. Okay, the first thing I'm going to add would be, let's find x and y. We know that x, the general formula for x was n1 x1 plus n2 x2, depends on how many nodes we have. And the general formula for x was, if you want to find any x or y, you need to multiply n matrix to x matrix, which is, this one is going to be the values of the nodes value, or the dimensional value, and then we can find the any other x inside. Okay, so we can do the same for y-axis. So general formula for any y between nodes is going to be n times y. Again, this y is going to be y values for node points, which usually are the endpoints of elements. Okay, and therefore y is going to be n1 y1 plus n2 y2, then continue, depends on the number of nodes we have. For two-dimensional cases, our x is variable of psi and eta, and it's going to be summation of 4 nodes, because we have node 1, 2, 3, 4, which I already colored them yellow. So ni xi, it is going to be n1x1 plus n2x2 plus n3x3, and finally n4x4. Let's put the value. Okay, for these shapes, quadrilateral shapes, if you remember, we extracted n1, n2, n3, and n4. Please go back to the lecture notes and remind yourself how we draw those or extracted those formulas. Let me write it here. n1 is 1/4 1 minus psi times 1 minus eta. n2, we found that to be 1/4. The first one is positive, the second one is negative, and 3 1/4, both summation, and finally n4 1 minus psi 1 plus eta. Okay, now let's put the numbers there. So n1, which is this one, let's write it here. I'm going to use a little bit lighter color. So 1/4 1 minus psi 1 minus eta times x1. Let's check what is x1. x1 is going to be 1 here, x2 is going to be 6, x3 is going to be 8, and x4 is going to be 3. It would be much better for me to write those values here. Let me write. So x1 was 1, x2 6, x3 8, x4 3. So much better. This is the vector for x, or nodal positions. Nodal y positions are going to be 1 1, not good one. It's going to be so 1, the other one is 1, 7 6, 7 6. Now we have better understanding. Okay, let's go back to the plugging the numbers, and x1 is 1 plus n2 again from here 1 over 4 1 plus psi 1 minus eta times x2. x2 is 6, so 6 plus n3 1 over 4 1 plus eta 1 plus psi and times x3, which is going to be 8, and the final one 1 over 5 1 minus psi 1 plus eta times x4. x4 is 3. Okay, if you multiply all these numbers to each other and add the numbers and the parameters to each other, you are going to finally reach this value 9 over 2 plus 5 over 2 psi plus eta. This is for x coordinate using psi and eta. We can do the same for y axis using this new normalized coordinates, and again they are going to be n1 y1 plus n2 y2 plus n3 y3 plus n4 y4, and we can easily plug the numbers there. Same, everything is going to be exactly same. This time, instead of using x1 x2 x3, we are going to multiply n1 n2 n3 and n4 with y1 y2 y3 and y4. I'm going to write first one, and the next ones you are going to do the writing. So n1 times y1 is 1 plus n2 is 1 over 4 1 plus psi 1 minus eta and y2 again is 1 multiply 1. Oh, let's write everything. It would be easier for me to write everything. 1 plus psi 1 plus eta times y3, which is 7, plus 1 over 4 1 minus psi 1 plus eta times y4, which is 6. Let's simplify it, and we are going to reach 15 over 4 plus 1 over 4 psi plus 11 over 4 eta plus 1 over 4 psi eta. So we reach these formulas for x and y, and basically our x and y direction are in terms of new normalized axis. Let's see what's the next step. Next step is very easy, because now we have x and y in terms of psi and eta, everything would be much easier for us. So let's find, because Jacobian, let me write the Jacobian matrix. Jacobian matrix is this: derivative of global coordinate over local coordinate. Global, local. Again, global, local, global, local. So this is Jacobian matrix. We need to find derivative of x over psi, x over eta, y over psi, and y over eta. Let's find them. I'm going to find them here. So derivative of x over psi using this purple formula, it is going to be just 5 over 2, the coefficient of psi. Derivative of y over psi, this one. So we have 2 psi here, one here, another here. So if I want to find that one, derivative over psi, it is going to be 1 over 4 for the first piece, plus 1 over 4 times eta. Done with this part. Derivative of x over eta, let's go and check that one. So eta is going to be just 1, okay. And derivative of y over eta, this time we have 1 eta here and 1 eta here. So it is going to be 11 over 4 plus 1 over 4 times psi. Okay, beautiful. These are the values I need to find my Jacobian matrix. Let's put it there. So this Jacobian matrix is going to be 5 over 2, 1 over 4 plus eta divided by 4, 1, 11 over 4 plus psi over 4. Okay, now I found my Jacobian matrix. But you know that we always use reverse of Jacobian. So let's see what is the reverse of Jacobian. I'm pushing a bit upward to have a little bit of space to write. So the reverse of Jacobian is going to be how should I write it? 1 over determinant of Jacobian matrix times, you need to change the position of these terms, and so it is going to be dy d eta, and here dx d psi, and for the other terms you need to just multiply with -1, so dy d psi but negative, dx d eta negative. So this is our Jacobian inverse Jacobian. If you want to have inverse Jacobian, that determinant, this one, should be a number, anything except 0. So let's calculate that one. So we need to make sure our determinant of Jacobian matrix, which is the variable of psi and eta, is not 0. So that value is going to be dx d psi times dy d eta minus the other two multiplied to each other, dy d psi times dx d eta. Okay, let's put the values here. Dx d psi is 5/2, dy d eta is 11/4 plus psi. Let's write it this time. 11/4 plus psi/4 minus dy d psi, which is 1/4 plus eta divided by 4 multiply x eta, which is 1. And if we simplify this formula, it is going to be 5/8 psi minus 1/4 eta plus 53/8. Okay, now we have determinant. Let's check for the node points. We have 4 node points. Node 1, let's write like this, eta psi. So -1 and -1, 1 and -1, 1 and 1, -1 and 1. Okay, these are the different nodes we have, and this is our Jacobian, which was variable of psi and eta. Let's put the values here. So for -1 and 1, it is going to be 25/4. So it is number, it's not 0. We're happy with it. Check. For 1 and -1, it is going to be 1, -1, 15/2. For 1 and 1, it is going to be 7. So check. And finally for -1 and 1, it is going to be 23/4. Check. So we have determinant for this Jacobian matrix, and we can use it later for our calculation. So usually questions, they ask for determinant in a specific point. For example, let's do it for a specific point. Let's find eta for the center of our element. So center of this element is going to be this point. So let me write the element center is going to be 0 and 0 local coordinates. Let's find Jacobian for that point. Where is it? So Jacobian for 0 and 0, if I write Jacobian 0 and 0, we already know Jacobian is based on our local coordinates. Let's find it. It is going to be, so let me show you which one I'm using. Basically, I'm using this matrix. So it is going to be 5/2. If I put 0 for eta, it is going to be 1/4, 1, and 11/4 when psi is 0. So for this local coordinate 0, 0, which represents center of our element, Jacobian is going to be this matrix. So let's review what I did here. I first start with generating x formula and y formula. So I generated formula for global matrix using local coordinates, global coordinates using local coordinates, and then I could easily calculate Jacobian because it's the derivative of global over local. Sometimes we don't go that way, and we have another option, which is calculating these items term by term, because we, as you remember, for when we say dx over for example, dx over, for example, dx or dy, you differentiate that item over n. That is why we have Jacobian. Let me write it. Explaining is sometimes a bit difficult. So I'm going to show you second method. So instead of finding x and then finding derivative of x, I'm going to find the items we have for derivatives of n. Let's see what I mean. We have derivative of x over, for example, psi. And when we say x, we know that x is n times vector, the nodal vector x. So, and I said we're not going to find derivative for x, so the only thing is going to be, because these x are constant numbers, so only we are going to find derivative for n. So basically this is n1 derivative of n1 over psi, n2 psi, n3 psi, and n4 psi. This is my matrix times the vector of constant nodal values, which is here is position. So instead of finding formula for x and easily find the derivative, this time I'm going to find these values and then go back and find these ones. Okay, so now you understand my strategy for this second method. So we are going to have the similar formula for x in terms of finding derivative over eta, which is going to be n nodal 1 matrix n1 over eta, n2 over eta, n3 over eta, n4 derivative over eta, and x1, x2, x3, and x4 vector. Let's see, let's write for y too. For y also I'm going to have similar point. Let's write this piece. Eta n2, eta n3, psi. Sorry, I'm sometimes making a mistake. This time it is going to be y1, y2, y3, and y4. And for y over derivative over eta is going to be derivative of n1 over eta, n2 theta, n3 theta, and n4 theta, y1, y2, y3, y4. Okay, let's see. The yellow matrix is exactly same for y here, and the green one, the green one here is exactly same here. So I need to just find derivative of n over eta once and then just plug these numbers. Let me make sure we know what is x1, x2, and x3. Where are them? Here. x1 was 1683. 1683. These are nodal values, and this one is 1176. 1176. So these are the constant numbers we have. So the major work we need to do is going to be finding derivative of n over eta and psi, and then finish it. So let's find derivative of n1 over psi. Let's check what was the formula for n1. So if I want to over psi, it is going to be negative 1 over 4. So negative 1 over 4 times 1 minus eta. N2 over psi is going to be 1 over 4, 1 minus eta. N3 is over psi is going to be 1 over 4, 1 plus psi eta. Let me check n3. N3 is this one. So derivative over psi is going to 1 multiply 1 over 4 multiply 1 plus eta. So correct. We made sure everything is in order. And n4 derivative over psi is going to be negative 1 over 4, 1 plus eta. Okay, let's find all these values for center of element. So 0 0, center of element, because I want to compare the values we found from the previous method with the current one. So if it's for center of element, eta is going to be here 0, and the value is going to be negative 1 over 4. This one is going to be again positive 1 over 4. This one positive 1 over 4, and negative 1 over 4. Let's do similar work for eta. This time it is going to be 1 over 4, 1 minus. Okay, let's continue finding the derivatives for n. Number 2 is going to be negative 1 over 4, 1 plus psi, 4.00, it is going to be negative 1 over 4. And derivative this time number 3, eta is going to be this time positive 1 over 4, 1 plus psi, it's going to be positive 1 over 4, and n4 4, 1 minus again positive 1 over 4. Okay, now I found all the derivative we needed inside this n matrix. So what are the x and y matrices, vectors? Let me show you x and y matrix. Let's use this time this color. So this is x vector and this one is y vector. Sometimes if you are reading some other textbooks, they use transpose form, which is instead of writing vertically, they use horizontally. Okay, so it is 1, 6, 8, 3 transpose 1, and y is going to be 1, 1, 7, 6. So basically we're saving a bit of space to avoid too much vertically losing writing space. Okay, now it's time to find derivatives of x over psi, which is going to be let me make sure I'm not making mistake. Which is going to be derivative of n matrix over psi multiplied by nodal position. Okay, so it is going to be, we already calculated derivatives of n over psi here. Let's put a number. So I'm using 1 over 4 outside, and so negative 1, positive, positive, negative. It's going to be negative 1, positive 1, positive 1, negative 1. This is my n matrix, which with derivative respect to psi, and x vector is going to be 1, 6, 8 and 3. If you multiply these two matrix and vector to each other, -1 multiplied by 1, +1 multiplied by 6, plus +1 multiplied by 8, -1 multiplied by 3, all of those summation multiplied by 1/4, it is going to be 5/2. Beautiful. Now I'm going to find derivative of x over eta, which is going to be derivative of n over eta, multiply these nodal values, and it is going to be again 1/4. For eta it is going to be -1, -1, +1, +1, and again x vector. Let's see, if you multiply those two, we are going to reach 1. Now I'm going to find derivative of y over psi, which is going to be derivative of n over psi multiply by y. Okay, so where is it? We have these derivatives for n, again similar to the previous one, exactly 1/4 -1. The second one should be positive, so let's copy exactly 1, -1. The only difference is going to be y vector, which is 1, 1, 7, 6. If you multiply this one, you are going to reach 1/4 derivative of y over eta, which is basically derivative of n over eta times y, because y is constant numbers and those are nodal values. 1, 1, 7, 6, and it's going to be 11/4. Beautiful. Now using these values, I'm going to find Jacobian. Jacobian is going to be derivative of x over psi y dx d eta dy d eta. Let's plug in the numbers. 5/2, 1/4, dx d eta 1, and finally dy d eta 11/4. Okay, now let's find inverse, which is going to be 5/2 times 11/4 minus 1 times 1/4. This is determinant, and we need to just swap the position of this two terms, and multiply with -1 the other two. Done. So we found inverse Jacobian. Let's check with the Jacobian we already found. I totally forget. Okay, let's check. This is the Jacobian we found using my previous method, and this is the one we found with the second method. They're exactly same. It's too much red, so yeah. And you know what is the next step? Whenever we had Jacobian and the derivative of n's, everything is going to be much easier, because let me continue with the calculation for strain displacement matrix. Let's start with compact version, which we said we are going to call it B prime, and the compact version of this matrix is dn1 dx, dn2 dx, dn3 dx, dn4 dx, and then the second row is going to be dn1 dy, dn2 dy, dn3 dy, and dn4 dy. This is our compact strain displacement matrix. And because all the formula we extracted for n are based on normal or local coordinates, so you need to multiply that with inverse Jacobian to be able to find derivatives based on the local coordinates, which should be pretty good right now with these changing coordinates. dn1 eta, dn2 eta, dn3 eta, dn4 eta. This is our matrix. Let's see. Let's put the values. The inverse Jacobian matrix is this one. So I'm going to use that one. So let's use the same color as the highlight. So it is going to be 8 divided by 53 times this Jacobian matrix, 11/4 minus 1/4 minus 1, 5/4. This is inverse Jacobian. Beautiful. And the rest, which is, we already calculated all the terms. Where are they? Here. So I'm going to just plug in all those terms. As you can see, let's use green for that. Dark green. So all of them is 1/4. So I'm going to take out that 1/4. So 1/4, and it is going to be 2/4. So in one side it's negative, so it is going to be -1. And two side positive, positive, negatives. Let's write positive, positive, negative. The other one negative, negative, two positives. Negative, negative, two positive, one. Done. Okay, let's do the calculation and multiply the 2 by 2 matrix, this one, by 2 by 4 matrix, which is going to lead us a 2 by 4 matrix. Let me write it. So this compact strain displacement matrix is going to be 8 divided by 53 times 1/4. So let's put the constant numbers, coefficients outside, and the other one is going to be 2 by 4. If you do the calculation, we are going to reach 5 by 2, 3, 5 divided by 2, minus 3, minus 1/4, minus 9/4, 1/4, 9/4. This is our matrix. If you want, you can go and multiply those coefficients inside. To just have one matrix, much simpler. So -5/55, 53, 6 divided by 53, 5 divided by 53, -6 divided by 53, 1 minus 1/106, minus 9/106, 1/106, 9/106. Okay, up to this stage we found compact strain displacement matrix. Now it's time to sub all these values to get final strain displacement matrix 4. Let's write the general formula for this. As you know, it is the combination of the values if we found for a compact one. Let me remind you what is the formula. The root of Schenck function number 1 over x 0, number 2 over x 0, number 3 over x 0, number 4 over x 0. So no, this one is 0 and 1 over y 0 derivative and 2 over y. Final line is going to be and 1 over y and 1 over x and 2 over y and 2 over x and 3 over y derivative and 3 over x and 4 y derivative of Schenck function number 4 over x. Let's put the values. We have all the values for those numbers, for those terms. For -5, 0, 6, let me check, 6, 53, 0, 5, 53, 0, negative 6, 50, negative 6, 53, 0, 0, negative 1 over 106, 0, negative 9 over 106, 0, 1 over 106, 0, 9 over 106, now it is going to be negative 1 over 106, negative 556, negative 906, 6 over 53, 106, and the last two is going to be 9 over 106 and minus 6 over 52. This is our strain displacement matrix. Okay, so basically I solved this question using two methods. The first I extracted my global formula based on local coordinates x and y, and using those two the formula generated was very easy, and I could find derivative of global matrix over local matrix, and Jacobian matrix was easily generated. And we checked for Jacobian to have inverse, so determinant shouldn't be 0. We checked for all nodes and it was okay. Later I said let's find Jacobian at the center of the element, point 0 and 0, and we found this value. Second time I said instead of finding formula for global coordinate x and y, let's write the formula for derivative of global matrix over local matrix. And when we extracted those formulas, we saw we have derivative of shape functions over local matrix, local coordinates, which is n1, n2, n3, n4 over psi and eta. So those derivatives. So we decided to extract those derivatives using the shape function formula we already know how to find. And for the center of element, I found the value for derivative of shape function over those two local coordinates. Then I simply multiplied those extracted matrix by local by node values for x and y, and we got the items we need to find Jacobian matrix, which is dx over d psi, dx over eta, a derivative of y over psi and eta, and we found those. So using those four terms, we could just sub in inside Jacobian matrix, and we found this one, which was exactly similar to the previous method. And again we found inverse Jacobian to make sure everything is okay. And later we said after finding Jacobian matrix, we can easily find strain displacement matrix, which is derivative of shape function over global coordinates. We said shape functions are not in terms of global coordinates, so we need Jacobian. We already know how to find Jacobian matrix using the previous two methods, and we multiplied inverse Jacobian by derivative of shape functions over local coordinates. We found those two matrix multiplied to each other, and we found compact strain displacement matrix. Later we just sub the compact one to the actual strain displacement matrix, and we found B. If you have any problem solving this question or understanding this one, you need to go back to session 4's materials. I already recorded a review video for session 4. Please watch it to make sure you completely understand, and then come back, read the lecture notes for session 5, and later you can watch this video and understand all the steps we took to find Jacobian matrix and strain displacement matrix. Next session, I'm going to tell you how we can combine these matrices and find the total stiffness matrix for the whole element, and find strain or stress for the matrix for the object or our design, which should be a very simple case. Okay, thank you very much, and see you next time.